Summer 2015 question 10 QP11. All right, so the diagram shows part of the curve y is equal to 8 over root 3x plus 4. The curve intersects the y-axis at A04. The normal to the curve at A intersects the line y is equal to 4 at the point B. The II part, which we are concerned, is that show with all necessary working that the areas of the regions marked P and Q are equal. Okay, so for the 2015 question on integration, as you saw there, this was a diagram that was given you. Okay, so the 10I part of QP11, as the question showed, wants us to establish that if the area under the curve, if the area P and Q is the same, we want to show that like the area P is also equal to the area Q. We want to prove that. That is what the question says, that we want to show all necessary working that the area of the region marked P and Q are equal. So how do you go about this? Now, remember that in this particular question where we have the integration, some bits of it have been solved in the other videos where we had the integration. We had the differentiation in this application, particularly the aspect that has got to do with the normal. Remember they said that the line x equal to 4 hits the normal to the curve, which is A, at point B. Okay, so when we use the information or the prior knowledge that we have about the equations of normals, point B can be found to have the coordinates. Can be found to have the coordinates 4 and 20 over 3. Guys, hope you're okay. So if you really want to know how we got the b to be 4, 20 over 3, remember that has got to do with the equation of the normal. And equations of normal fall strictly under differentiation, and that is solved in the differentiation video. So we'll just proceed from this point that the point B has got the coordinates 4, 20 over 3. In any case, too, you can also in your private practice try and use the whole concept to try to see how we can show that the coordinate is B. But that's not the focus of the question. The question just wants us to show that with necessary workings that the area P is equal to the area Q. Now, guys, watch. Now, if you look at this carefully, you realize that you have the area under the curve being P. Okay, so the area under a curve P, the area under the curve, okay, bounded by this point A, and that point is going to be P. Okay, and Q is also the region above the curve that is also bounded by the line x equal to 4 and also the normal AB as we are shown. So if we are being told that we should prove that the area P is equal to the region, like the area of the region P is equal to the area of the region Q, what it therefore means is that, now look at the shape that we have here, okay? Have you seen this shape? What kind of shape do we have that in geometry? That is a trapezium. Do you see a trapezium? Okay, so it means that if you take the area of the trapezium here, like AB to that side, the area of the trapezium, that area of the trapezium should be equal to, okay, should be equal to this area and that area. Are you okay? The sum of P and Q should give us the area of the trapezium. Hope you understand that, because the trapezium is made up of those two parts. Now, if P is the same as Q, remember P is the area under the curve y is equal to 8 over root of 3x plus 4. That is the area under that curve is P. So if P is the same as Q, then what it means is that 2 times the area under the curve should give us the area of the trapezium. I'll take it again. P is the area under the curve. Y is equal to 8 over root of 3x plus 4. So if P and Q are the same, then what it means is that the area under the curve, which is P, is the same as the area under the curve, which is what? Q. So twice the area under the curve should be equal to the area of the trapezium. Hope you understand that. All right, so proceeding from that footing, let's go ahead and see how we can establish that. So we want to find the area under the curve that is bounded by the x-axis here. So we know from our basic integration that if you want to find the area under the curve bounded by the x-axis, what do? We have to integrate along the x-axis. So you integrate the function 0 to 4 because it's 0 to 4 on the x. Then the function is 8 all over root of 3x plus 4 dx with respect to x. Hope you are fine. So that is how you do so this is what we have to do. Remember, in the examination, you can have your calculator, and this is a definite integral, so you can just put it in there and work out the values. But for some of you who are missing, or you've lost a bit of your understanding on how these things work, guys can go back and look at our revision course on integration and see how best you can integrate such a function, okay? So, but let me just go in a bit of that. If you want to integrate something like this, you know the principle of integrals of linear factors. That is, when you want to integrate a function of the form ax plus b raised to the power n dx. Okay, you remember how to do that? Okay, the rule is very simple. We are saying that the result of an integral where n, okay, like ax plus b raised to the power n of this sort, what happens? You're going to have ax plus b raised to the power n plus 1 all over n plus 1, okay, times a. Then you put your arbitrary constant there. So that's what you have. Ax plus b all to the power n plus 1 all over n plus 1 times a, then plus c. So when you have that, that should give you your integral. So if you apply the same principle, like I said, to this, the area of the curve that is bounded by the x-axis, 0 to 4, okay, upon clear calculations and integration, you have to get 32 over 3. So that should be the integral of that, 32 over 3 square units. So this is the area of P. All right, so now we are saying that 2 times this should give us the area of the trapezium. So let's look at the area of the trapezium. So area of the trapezium. I have area of a trapezium. We know what the rules of a trapezium is. Half sum of the parallel sides, okay, times height. So half times the parallel sides times height. So when you look at it, the parallel sides is going to be this side and that side. Are we okay? And the height is going to be from there. So we are going to have half. What is going to be the parallel sides? The part that goes on A, okay, is going to be 4, okay, plus B, and B is the part that goes onto the y-axis. So that distance there, and that comes from the coordinate of B, which is 20 over 3, times the height. The height is going to be there. So we are going to have the height being 4. Hope you are fine. Okay, so when we deal with that, we should get 2 into brackets, that's 12, so you're going to get 32 over 3. So guys, if you look at it carefully, the area of the trapezium is 2 times 32 over 3. Now look at the area of the curve that is bounded by the x-axis. We also have 32 over 3. So as we said from our very beginning, that if we want to show that this is the same as this, which means twice 2 times the area under the curve, okay, or 2 times p, should give us what we get for the trapezium. And it is obvious. If the area under that is 32 over 2, so we can just say that 2 times p, which is 32 over 3, should be equal to the area of the trapezium, which is also 2 times 32 over 3. So clearly, we have been able to establish that the area of the region P is the area of the region Q. So for summer 2015 question 10II QP11, that is how we are able to use the integration aspect of area under curves to resolve the problem at hand. Question 1 QP12 summer 2015. The function of f is such that f prime of x is equal to 5 minus 2x squared, and 3, 5 is a point on the curve y equal to f of x. Find f of x. So for question 1 of QP12, the variance, the function f is such that f prime of x has been given. So let's look at that. F prime of x has been given in the problem. Okay, so f prime of x, as the question shows, f prime of x is given to be 5 minus 2x squared, okay? And we are saying that 3, 5 is a point on the curve, y is equal to f of x. So we are saying that 3, 5 is a point on the curve, y is equal to fx. Now the question wants to find f of x. Now this problem actually, as was shown, is one of the areas that usually is tested in your exam. It has got to do the equation of a curve, okay? So anytime you are given a first derivative, okay, and you are required to find the equation of the curve, guys, note that it's an integration. You have to like bring the derivative backwards. You have to reverse the derivative. And remember, integration is anti-differentiation. So any process that seeks to reverse a differentiation is an integrative process. Makes sense? So you have a first derivative given, f prime of x equal to 5 minus 2x. And we want to find a particular equation, the f of x. So it means we need to reverse the derivative. And like we said, an anti-differentiation is an integration. So we integrate 5 minus 2x squared with respect to x. The reason being that the variable is in x. So we have to integrate it with respect to x. Now when we do this integration, we are going to get y is equal to, okay, 5 x minus, you know what to do. So minus 2x, you add 1, 3, all over 3 plus c. Okay, the c is our arbitrary constant. Remember, if you're having a bit of challenges or you forgot to just go back to our website at learnwestafrica.com and try and pick up the revision courses on calculus and integration. I'm sure that it should bring much of these things back to memory. So the y is going to give us 5x minus 2 over 3 x cubed plus c, where c is arbitrary constant. So this is the equation that we have. Now you have to find the value of c, because it is when we know the value of c that we can have the definite nature of the equation of the curve. But we are saying that this derivative is being observed at the point 3, 5, where 3 is going to be the x coordinate for that point, y is going to be 5 is going to be the y coordinate. So we just slot 3 and 5 into this equation so that the c will appear. Are we making sense? All right. So if you do that, you can say that at the point 3, 5, your c, no, I just cut that part out because it's just a bit of some simple algebra. Your c, okay, guys, should give you 1. So you can try that. If your x is going to be 3 and your y is going to be 5, what is going to be the value of your c? Your c is going to be 1. So now that you have your c being equal to 1, we can say that the equation of the curve, ladies and gents, the equation of the curve is going to be y is equal to 5x minus 2x cubed over 3 plus 1. Okay, so that is a very simple problem that was tested in question 10, QP 12. Question 1, QP 12 of your problem in summer 2015. Question 10, QP 12, 2015 summer. The equation of a curve is y is equal to 4 over 2x minus 1. I. Find, showing all necessary working, the volume obtained when the region bounded by the curve, the x-axis, and the lines y is equal to x equal to 1 and y x equal to 2 is rotated to 360 about the x-axis. Okay, so for question 10 is a question on volume of revolution, volumes of revolution around an axis. That is what you saw in question 10. Pretty, very simple. When you see that, you don't need to panic. Very, very simple. When we just mention volumes of revolution, what do we mean? You just have to kind of integrate the whole function with a square. Okay, so you square the function and integrate it, and you multiply by pi. That is kind of a radial measure in there. So that's just simply what we mean by volume of revolution. Just integrate it, the function, the square of the function integrated, then you multiply by pi. That will give you the answer for that. So the problem mentions that. Let's look at the function that was given. So we're saying that y is given to be 4 over 2x minus 1. Guys, right? That's the problem. Y is equal to 4 over 2x minus 1. And we are being asked to find, showing all necessary working, the volume obtained when the region bounded by the curve, the x-axis and the line x equal to 1 and x equal to 2 is rotated to 360 about the x-axis. So what do we mean? So we have the volume, okay? The volume being, the volume that we want to find is going to be pi, okay, 1 and 2. Remember how you're saying 1 and 2 because if we are going to integrate, find all the integral values around a boundary, and the boundary point has been given to be x, the line x equal to 1, x equal to 2. So that is our starting point. So this one's going to be our lower limit, that's going to be our upper limit, okay? And the curve that we are being given is 4 over 2x minus 1 all squared, okay, with respect to x. So that should give you the volume of revolution 360. That is what you should have. Okay, so what happens to that? We need to integrate that with respect to x. So we are saying that about the x-axis. That gives a very simple integral. Now this is a definite integral, so we don't have any challenges with it. And like in the previous question, I've already shown you how you can do the integration of the linear factors, okay? When you have a linear factor, 2x minus 1 all squared, you take it up, you're going to have 2x minus 1 minus 2, then you slot the values in there. Pretty simple for us to do. So when you're able to resolve that, you should get 16 over 3 pi. So this is going to be your volume that will be generated when the curve is the solids of revolution. If you do that, the volume should be 16 over 3 pi. So just try and do the integration of linear factors, and I'm sure that you should also, that should confirm 16 over 3 pi as our answer to this part. Question 2, QP13. A curve is such that dy dx is equal to bracket 2x plus 1 all to the power half, and the point 47 lies on the curve. Find the equation of the curve. Okay, so for QP13 2015 question 2, the problem that was given there, we are saying that a curve is such that is dy dx. Okay, so this is what we have. Okay, so dy dx, okay, is equal to 2x plus 1 raised to the power half, right? Raised to the power half. And we are speaking that we are making this observation at a particular point 47, which lies on the curve. The question wants us to find the equation of the curve. Pretty simple. An anti-differentiation. You have to reverse the derivative process, and a reversal of differentiation process is integration. So we integrate that. Integrate 2x plus 1 raised to the power half with respect to x dx. So what do we do? Now this is a linear factor. This is a linear factor where we want to integrate, so we know what to do. You just add up. All right, so let me just take you a bit through the process. So for integration of linear factors, first you take 2x plus 1, then you have half. You add 1 to it, so we're going to have half plus 1 all over your new exponent, which obviously is going to give you 3 over 2 times what you get in there, 2 plus c. Are we okay? Okay, so that's what you do. 2x plus 1 to the power half, linear factor. You add 1 to it, then the denominator, 3 over 2 times 2, 3 over 2 times, you differentiate what is inside, and that's going to give you 2. All right, so when you resolve that, this is going to give you 2x plus 1, 3 over 2, okay? 2x plus 1, 3 over 2, all over 3, okay, plus c, and that should give you y. No qualms about that, right? Okay, so we are saying that this point 47 lies on this curve. So what do we do? Wherever we find x, we put 4 there. Okay, and wherever we find y, we put 7 there. So when you do that substitution nicely, okay, when you work that substitution out, you should have your c being equal to minus 2. So I'll leave you to try and justify and establish that. Your c is going to give you negative 2 when you have your x being 4 and your y being 7 being inserted into that. Okay, so c is equal to minus 2. All right, so when you do that calculation very well, what happens? Your y is finally going to give you 2x plus 1 raised to the power 3 over 2, okay, all over 3 minus 2. So this is going to be the equation of the curve that was required of us in question 2, QP13, summer 2015. Y equals to bracket 2x plus 1 to the power 3 over 2, all over 3 minus 2. Question 10, QP13. points A, 2, 9, and B, 3, 0, lie on the curve y is equal to 9 plus 6x minus 3x squared, as shown in the diagram. The tangent at A intersects the x-axis at C, showing all necessary working. II, find the area of the shaded region ABC. Okay, so for question 10, QP13, the part that is relevant to our discussion, which is the application of integration, is the diagram that was given. I'm sure you might have seen the diagram, some aspects there. Okay, so that is it. Now, this is the diagram that we're given, and the shaded portion was shown here as you find in here. Now, let's just go to some of the facts as the question was just flashed onto your screen, but I'll just take it again. It says that the points A, 2, 9, as you find here, and 3, 0 lie on the curve. So 3, 0, B, okay, lie on the curve. 9 plus 6x minus 3x squared, as the question was read out, you saw that. And we are saying that the tangent A intersects the x-axis at C by necessary working. We want to, our focus is the II part. We want to find the area of the shaded region ABC. We want to find the area of the shaded region ABC. So like we are saying, so we should want to find the area of the shaded region. That's there. So that's important now. So what do we do now? We know from our understanding of tangents, okay, now if you want to find the area of the shaded region, you need to know something. Remember from the revision courses that we took, it has been established. When you have things of this nature, you can think of an imaginary line here, okay, division here. So we try to find the area, okay, of the curve, all right, the area that is bounded by the equation, by the tangent and that, okay. Then we also look at the area that is bounded by the curve and the x-axis from this point to that. Then we will subtract. I'll take it again. If you look at it, this is the tangent. The tangent cuts the x-axis at point C. Okay, so when we know the area of the triangle that has been created there, and that area of the triangle is the same as the area bounded by the tangent and the, how do you call it? The area bounded by the tangent and the x-axis, okay? Then we now find the area that is bounded by the curve and the x-axis, which will be this region. So when we subtract the area that is bounded by the x-axis and the curve from the area of the triangle, we should get the area of the shaded portion. Are we okay? So it should be pretty simple for us to work this out, guys. Pretty simple for us to do that. Now, if you look at it carefully, what we then need is to find the coordinate of C, because it's when we know the coordinate of C, then we can find the area of the triangle, or the area bounded by the tangent and that. So how do you find the equation of a tangent? Now, from our previous discussions on differentiation and how to do that, you can use the same principles here, where you try and differentiate the curve, okay, at the point 2, 9, and use that the equation of the 1-point formula to find the equation of the tangent. But that's not our focus. So we will just try and import the equation of the tangent. So the equation of the tangent, if you're able to go through that process, and I charge you to do that, okay? Yes, prove that to yourself, that the equation of the tangent is y plus 6x is equal to 21. Y plus 6x is equal to 21. So if that is the equation of the straight line or the tangent, what is the coordinate of C? So you need to find the point at which the tangent will cut the x-axis. And where the tangent hits the x-axis, you have y being equal to 0 on the x-axis. All right, so when you work that out, your x should give you 3.5. Because y is equal to 0, you're going to have 21 over 6, so that should give you 3.5. Guys, hope you're okay. I'll give you 3.5. So point C has the coordinates 3.5 and 0. Now, some of you may choose to use an integration to integrate the tangent, okay, from 2 to 3.5. That is fine, from 2 to 3.5. But it is also obvious that this is a triangle. So for a triangle of this nature, what do we do? Half base times height, okay? Half base times height. So you can see that the area of the triangle, okay, let's use that to represent the triangle. The area of the triangle should be half base times height. So half times the base. Remember, this is 2, That side is 3.5. So the difference between that is what? 1.5, okay? So half times 1.5. That's the base. Because the x component here is 2, and that is 3.5. Hope you are fine. So the difference between 2 and 3.5 is 1.5. And what's going to be the height? The height is going to be this, like up to the y-axis, which is 9. So half 1.5 times 9. That's a very quick way to arrive at it. Some of you may choose to integrate the line y plus 6x equal to 21 and use the limits of 2 and 3.5. That is okay. If you want to do that, that is okay. No problem. But you can also take the easier route. Once a straight triangle has been established, half base times height, as we know from geometry. So half times 1.5 times 9. That should give us the area of the triangle. Are we okay? Are we okay? So when we're able to do that, we should arrive at our triangle. Let's call that A1 being 6.75 square units. Okay? 6.75 square units should be the area of the triangle here. Or the area that is bounded from the point A, like the tangent from that point with the x-axis should give you 6.75 square units. We are cool. We are cool. Good. So now let's look at the area of the curve that has been bounded by the x-axis. So when you take the area of the curve that is formed by the x-axis and the curve and the x-axis, what happens? Look at your integrals. So you're going to have 2 to 3. Okay, so that's going to be your lower limit. You're going to integrate from 2 to 3, then you have the equation of the curve. So A2, remember, A2 is going to be the area of the curve and the x-axis from the points that we are interested. So we are going to have 2 to 3. And what's the area of our curve? Like the equation of our curve, 9 plus 6x minus 3x squared dx. Any problem with that? Any problem? All right, so when we're able to do justice to that, we should get 3 square units for the area A2 that has been bounded by the curve and the x-axis. So now what is the area of our shaded region? 6.75. That is for the triangle minus that for the curve. Therefore, the area of the shaded portion, ladies and gents, should be 6.75 minus 3 square units. And that should give you 3.75 square units. Okay? 3.75 square units. So we should be good to go. And that is it for question 10 QP13 summer 2015 II, where we were asked to find the equation, the area of the shaded portion. That is how you go to it.